Hey everybody, welcome to the Chapter 5 Excel problem. This one is a doozy. I think the technical term is it's a big funker, a big old problem. And the concept of the time value of money is a little bit confusing anyway. It doesn't have to be, and over time it becomes easier, but when it's new, it's pretty confusing. The idea is this: if I have a certain amount of money now, we'll call that now the present value, and then I hold that money for a certain amount of time, and I earn a certain amount of interest on it, then at some future date, it'll be worth a larger amount. And that's the present, I mean, the future value of it. So the present value is money we have today. And the future value is the money at some future date when time and interest have worked on it. If we can do the math to figure that out, we can also do the math to say, hey, if I want some given future value, and I need it in a certain amount of time, and I can earn a certain amount of interest, how much money do I need today for it to add up to that future value? And then we can also say, instead of some single amount, how much would I have to make in payments each year for so many years or whatever. So that's the kind of the broad concept of the time value of money. So let's take a look at some of these problems. So this first one here, um, we know that we have an investment of $1,000, an interest rate of 10%, and we have it for 4 years. So presently it's worth 1,000. The question is, what will it be worth at the end of 4 years in the future? So to find this, so first of all, just so you know, like all of these future value, present value things, they often get wacky with um, like negatives. Payments are considered negatives, and then it gets confusing. So what I do is I always use the absolute value, ABS. There might be some specific transactions where I wouldn't, but generally I do. So I always put ABS first, equals ABS, which means the absolute value, which means no negatives. Okay. And then I use the formula FV for future value. And then we can see for future value, the arguments are the rate. So I'm going to just click on the rate here, 10%. The number of periods. So I'm going to click on the 4 here because it's 4 periods of a year each. And then this is a little confusing too. Payments would mean if you're making a payment each period, okay? And that isn't the case. Here, we're just taking $1,000 and putting it at the beginning, and then not paying any more going into the future. So I'm going to put 0 for PMT or payment. And finally, for present value, I'm going to click on 1,000 here. So what we're saying is, hey, Excel, what is the absolute value of the future value at 10% of for 4 years, with $0 being added after that first year and having $1,000 at the beginning of the whole thing? What is the future value of that? And the answer is $1,464.10. So if I put $1,000 in the bank and I can earn 10% on it, and it sits there for 4 years, I will have $1,464.10 at the end. Okay, so that's the process we're using here. So part B wants us to create a table with future values at various interest rates and time periods. So our interest rates are 0, 6%, and 25%. And then our time periods are 0, 1, 2, 3, 4, 5. Okay. So I'll show you how I'm going to do this. I'll say this equals the absolute value. Like I said, I just put absolute value to make it so there's no negatives of the future. So then we do future value. And then for rate, I'm going to click the 0. For the number of periods, I'm going to choose, in this case, 0. The present value, is oh, wait a minute. You know what I'm going to do for this first year? Sorry. For the first year, because it's year 0, meaning the start of all of this is just 1,000. Right? They're all going to start in that same way. We could just type in 1,000, or I could say this equals 1,000. All right. All right. So now here we'll say this is the absolute value of the future value at 0% interest, number of periods, 0 payments. We're just letting this money compound. We're not adding to it. At a present value, and we'll see that at 0% interest, that $1,000 will turn into $1,000, right? Because it's not earning any interest. And we could do that all the way down. It's going to be 1,000. Oh, I'll do that in a minute, but I'm going to show you like, so if it was at 6% though, we would say this equals the absolute value of future value. Rate and now is 6%. Number of periods, the row we're in. Payment is 0 because we're not making any additional payments. And the present value is this $1,000. Or we could put it up here too. Oops, I keep forgetting to put that second one. So second closing parenthesis. All right, so here you can see if we make 6%, that it grows to $1,060. And then on this one, we'll say this equals the absolute value of the future value, rate, oh, sorry, 25%. Number of periods, again, we just use the year we're in. Payment is 0. Present value is 1,000. So we can see when we're earning 25%, that grows to 1,250. So now we could keep entering all of these things in, and it's pretty slow process. Okay, or we can use a couple little tricks here. So some of you probably know how to use the fill tool with Excel, where we can grab this little nail in the lower right-hand corner. And you see it makes this black plus, and when we click on it, we can then drag it down and it will fill the formula in. The problem is if we do that, it's going to adjust our formula. And in some ways we want it to adjust, in other ways we don't. So if I do this, you'll see it messes everything up. So it adjusts my formula. So here you can see I'm looking at C11, A13, 0, and C12, which is exactly where I want to look. But then it assumes I want to look at C12, A14, 0, and C13, which is not what I want to do. So what it does is it kind of slides the formula down with you. So instead, though, I can tell Excel for when I use the fill tool, I want you to leave certain cells fixed, okay? And I can do that by saying, I want C11, which is my interest rate. I want that to stay put. So I tell Excel that by putting a $sign on either side of the C. That locks it in. So now when I use the fill tool, that cell will always stay C11. But this one over here, my number of periods, I want that to go and increase so that in this next year, I want it to be 2, and the next year, 3, 4, 5. So I'm going to leave that one as A13. And then when I fill, it will assume A14, A15, A16. Finally, C12, which is my present value, I want that to stay fixed as well. So I'm going to tell Excel to do that by putting $signs on either side of the C. Now, I know that seems like a lot, and you'd be tempted to just say, screw it, I'm just going to type it all in. But I'm telling you, it is a great skill to learn that will make your life so much easier in the future. So take the time to learn how to do it. Now, if I grab this little nail and I just drag down, it just fills all that for me. And you can see it left my let's see, my interest rate fixed on cell C11, which is my 6%, but it changed my number of periods so that it filled down with it. And then it left um, my present value fixed on cell C12. And that's so much faster, right? So I'll do the same thing. I'll say stay fixed on D11, stay fixed on D12. Then I can use my fill tool. I can do that one more time here. Stay fixed on B11. So these little Excel tips and tricks are worth taking the energy to learn. We would expect this first one to stay 1,000 all the way down because it's earning 0% interest. So now we can see the difference, right? If I start with $1,000 and earn 0% interest for 5 periods, I still have $1,000. If I start with $1,000 and earn 6% interest for 5 periods, I have $1,338.23. If I start with $1,000 and earn 25% for 5 periods, I have $3,051. It's a pretty huge difference. So the next thing it wants us to do is create a graph um, uh, with the years on the horizontal axis. Okay, so what we're going to do is we're just going to kind of highlight just like that. Then we're going to come up to insert, and we can kind of play around with it, but we can sort of look at some of the options we have here. And we can see that one looks pretty good. That one's kind of weird. That one, though, looks just about perfect. So what this does is it gives us a chart, and you could put a title and stuff on it if you wanted to. I'm not that worried about titles. We could also, probably if we'd highlighted these, it would have put those as our series titles. But we can see, right, here's series 1, which is our 0%. And so that stays flat. Series 2, which is our 6%, and then series 3, which is our 25%. In fact, if we wanted to get those labels in there, like I said, we could probably just do that. Hit insert. Well, that one's doing some weird stuff when we include that. So I think it's best to just highlight that. Of course, you can play with these to get them exactly how you want them, but that one's pretty darn good. All right, so let's look at number C. Letter C? I guess letter C. C is not a number. So now we're going to find the present value. So in this case, we know we want to have $1,000 at some point in the future, when 4 years from now, and that we can earn 10% a year during that amount of time. So all we do, like I said, I like to use absolute value, so I don't get any weird negatives. But I'll say this is the absolute value, and then I use the formula PV for present value. And again, you can see Excel gives you the arguments, or meaning the numbers that you're going to put in there. So I'm going to just click on rate. My rate is 10%. My number of periods, 4. Again, payments are 0. We're not making payments each year. We're just going to have one amount, and that's the future value. So we're going to put 0, comma, and then the future value for 1,000. Oops, again, I didn't put a second closing parenthesis. But luckily, Excel caught it and warned me. So there we go. What this means is if I will take $683.01, and if I can earn 10% on it, so put it in the bank, earn 10%, then at the end of 4 years, that would be worth $1,000. I'm going to pause my recording for just a second. I don't know what it'll sound like on your end, but I'm just going to get her have a drink of water. Okay, I'm back. I don't even know what it sounded like. May have just sounded like nothing to you. Anyway, so D, we're going to find the rate of return provided by this investment. So now I have an investment that costs $1,000 and it will be worth $2,000 in 4 years. So we need to find the rate of return. So we have a special formula in Excel. It's called RRI. So it equals RRI. I click on the number of years for the NPER, which is number of periods, the present value, and the future value. Bam. That's pretty easy, right? All right. E, calculating the number of years required to double a population. So this is similar, okay? So we're going to start, we need to find the doubled population. So if our current population is 34.2, I'm just going to say this equals the current population times 2. So that's our doubled population. It's just the current population times 2. And then we need to figure out, like, the number of years it takes to double that population. So there's an Excel function called NPER for number of periods. And for that, we're going to do our rate, comma, and then for payment, we're just going to put 0. Again, that would be like, this is not an exact fit for this problem, but it would be like if we were like adding more people or taking more people out, or in this case, be adding people each year, and we're not doing that. I mean, we are, but it's at this steady rate in between. So just put a 0 for payment. And then we're going to put our present value is 34.2, and our future value 68.4. Ooh, it didn't like that. So let's see. Let me double check my notes and see if I did something wrong. So, oh, you know what? I'm going to do this again. Equals absolute value. Oops, I'm doing it in the wrong place. So I think I should have done this as the absolute value of all of that. And I think it wants us to do our current population. Yeah, so this is a little weird because what we're doing is we're kind of reusing a financial function to figure this out, I guess, in a non-financial problem. So it wants us to consider our present value as a negative. In real life, we often do things like that because it's the amount of money like we're paying out at the beginning of an investment, and then the amount that we're getting back at the end. But it's confusing because we don't really have a negative population. Nonetheless, this is how we set it up. So the absolute value, and then we use the number of periods function, and we just have to do a negative in front of our current population. So I always say, if I can't understand the why of something, hopefully I can at least figure out how to do it. And then in time, if I use it enough and I need to, I'll figure out the why. And if I don't, good enough. And I know with these problems, sometimes you're like, why are we learning all this? These are valuable concepts to understand, even if you don't remember the exact process. The idea that we can sort of forecast what things will be in the future or how many periods of time it will take to double something. So we're thinking analytically, even if we don't remember the exact process, that's important. And also just becoming more comfortable using Excel as a tool because any of you who are going to continue in business, you're going to use Excel more and more. You may not have to use all these functions, but you should just be comfortable working in Excel. Uh, if you're an artist, this is your medium, I guess, so to speak. All right, so F, we're going to find the present value and the future value of an ordinary annuity. So to this point, we've always been dealing with the present value or future value of a lump sum, where I take like $1,000 and say, what will be worth that will be worth in 4 years? Or I say, if I want $1,000 in 4 years, how much do I have to have available today and let it grow with interest? So an annuity is where we make payments each year. And so it might be a question of like, if I'm going to pay $1,000 a year, what will that be worth in 4 years if I'm earning 12% on it? So let me show you how to do that. So we're going to hit equals. And again, we'll do the absolute value. And then we're trying to find the present value of this annuity. So PV is present value. And then the rate, comma, the number of periods. And now we're going to use this payment. So for where it says PMT, we're going to do $1,000. So what this means is $1,000 per year for the next 4 years. In today, because we know at the end of 4 years, that's going to be worth more money than it is today. Okay, but in today's dollars, that'd be worth $3,037. So this is what they do for when people like win the lottery, right? They say, do you want to get the whole amount in 4 years? So in this case, $4,000, or do you want to get $3,037.35 a year for the next 4 years? That's what this calculation would show. So the future value would be like, hey, if I put in the absolute value of the future value, if I put in $1,000 a year at 12%, 12%, 4 periods of time, payment of 1,000. At the end of 4 years, that would be worth $4,779. So the $4,000 I put in plus $779.33 in interest. Okay, G, recalculating the present and future values for part F if the annuity is an annuity due. So this is a little bit weird, but all it means is typically when we use these future value and present value functions, it assumes that we're getting the money at the end of the year. That's pretty normal. So it's been working on it, the interest's been working on it for that year. But when we have an annuity due, that means we're paying to someone else. Typically, we're expected to pay at the beginning of the year. So all we do is we use the same function, okay, ABS, absolute value of the present value. And then I do number of periods. I hit 4, comma, payment. I'm sorry, number of period. Wait, did I do something? Oh, sorry, it should be rate, comma, number of periods, comma, payment, comma. For future value, we usually just leave it blank, but in this case, we're going to hit 0. And then for type, we've been just leaving it blank, which means 0 for end of the period. But in here, we're going to enter 1. This means it's a payment for the annuity paid at the beginning of the period. That's the only difference to what we did up above. Oops, and I still didn't put a second closing parenthesis. Same thing for the future value, equals the absolute value of future value with the rate and a year or number of periods and a payment amount, a 0 and a 1 instead of leaving that blank. There we go. Okay. So now it says recalculate the present value and the future value for parts A and C if the interest rate is semi-annually compounded. So now, instead of us earning 12% per year interest, okay, we'll be earning 6% per semi-annual period. And what that means is that we're going to be getting a little bit more interest just because we're going to compound it twice a year instead of once per year. So, but we don't get the full year's worth of interest each time we compound it. We just get half of that. Okay. So to find the future value, I'm going to say equals the absolute value of the future value. For my rate, I'm going to click on, actually, I'm going to put another parenthesis and I'm going to click on my interest rate and then hit a slash for divided by 2. So I'm going to divide my interest rate by 2. And then my number of periods, I'm going to put another parenthesis and I'm going to click on my number of years and then multiply that by 2. So what I'm saying is I could just type it in, right? I could just type in half of 12% is 6%, and 2 times 4 years is 2 times 4 is 8 semi-annual periods. But I just like to use these functions so that if I ever need to go in there and like change, I can change any of these arguments up here and it'll redo all the calculation for me. It's like creating your own calculator. So it's our rate divided by 2 and our number of periods times 2, because now we're getting half of the amount of interest per period, but double the number of periods. Our payment, let's see. So this is back to part C, okay, where it wasn't payments, it was just a single amount. So I'm going to say the payment is 0 and the present value was 1,000. Let's see. Something feels off about that. Let me make sure I did that right. Well, you know what's off? I said I was using these amounts down here instead of the amounts from part C. So it's not, I'm going to redo this. Equals the absolute value of future value, because we're doing this for parts A and C. So for rate, I'm going to go all the way up to C, get that rate divided by 2. Number of periods, how about I get that number of periods times 2. My present value is 0. I'm sorry, my payment is 0, and then my present value is 1,000. Okay. Guess what I did? I did it in the wrong cell. Sorry, guys. Okay, I'm having a hard time here. So do it one more time. Equals the absolute value of future value of rate for C divided by 2. Maybe I'm messing up on purpose so you guys get to see this 3 times over to get good at it. But that's not really true. I just messed up. All right. And then the number of years times 2. Present value is 0. I mean, payment is 0. Present value is 1,000. All right. I think that's right, finally. But for the present value, we do the same thing. So equals the absolute value of the present value, where the rate is the rate in C divided by 2. The number of periods is the number of periods in C times 2. Future value is a 0. I did it again. The payment is 0 and the future value is 1,000. All right. So that means you can see up here when we are in C, if we want to have $1,000 at the end of 4 years, we have to invest $683.01 and then have it earn 10% for 4 years. But if we can compound it semi-annually, so it's getting interest every 6 months, even though it's the same amount of annualized interest, we're actually it's 676,084 or $676.84 that we can invest. So you can see that little difference, $6, a little less than $6, just by compounding more often. Okay, I'm going to pause this again and get another drink. I don't know if you hear anything while I do it. I know you don't hear it while it's paused, but if the pause sounds like a break. All right, hold on. Okay, here we go with part I. We're making progress. I told you this was a big honker. Okay, so finding the annual payments of an ordinary annuity and $1,000 annuity due. So now we're going to use a function called PMT for payment. Pretty easy. We just put equals PMT. And the first one's an ordinary annuity. So for rate, we're just going to click on the rate here, 8%. And then number of periods. This one is 8 for 8 years. And then our present value. And that's it. So if we, let's see, so if we have an annuity of $1,000, it will pay us $174.01 a year for the next 8 years. Okay, so annual payments for an annuity due is similar. We just use PMT, and then we do the rate, comma, number of periods, comma, present value, comma. We're going to do a 0 for future value, and then when we get to type, instead of leaving it blank like we have in the past, we're going to change that to 1, meaning we're going to be paying on this at the beginning of the period. So that's going to change the amount to $161.12. Okay, part J, finding the present value and future value of an investment that makes the following end of year payments. So this one is a little bit wacky. In fact, this stuff wasn't even on here. Those were notes I made when I was looking at this one earlier. So this is what it would look like on your spreadsheet. There's a couple of ways to go about doing this. So the present value is pretty easy because we have something called net present value. So we just hit equals NPV, and then we just click on the rate, comma, and then we highlight the payments. And that's it. So that will tell us the present value of future payments of 100, 300, and 600 over the next 3 years. Unfortunately, there's no version of this for future value. There's not like a net future value. So those notes you saw I had typed in there is if you just take the future value, and in essence, we go like equals future value, and then we go 8% for the rate. And this is where it's a little confusing. So this first year's payment, we're going to get it, and then we're going to have it for 2 more years. Okay, so we're going to say 2 years, and then for payment we're going to put 0. I'm not for payment, sorry, for Yeah, for payment, we're going to put 0. And then for present value, because it's a payout, this is what's so hard, why this one's so hard. I'm going to put a negative amount for the payment. We could also accomplish the same way. I guess I should have done it like I've done all the other ones. In fact, I will. So that was one way, or we could say absolute value of the future value of this rate, comma, 2 periods, payment of 0, and a present value of $100. Then for the second payment, I'm going to say it's the absolute value of the future value of rate 8%, number of periods 1, payment 0, present value 300. And then I could do all that again for this third year, but this is money I get at the very end, so it will just be worth, its future value will be 600 if I get paid at the end of the third year. So that's 600. And then to find my future value, I say it's this much plus this much plus this much. It's the sum of my future values. So that one's a little bit harder. And I would tell you, don't worry too deeply about why. But if you want to dig into it deeper, you certainly can. All right. Whew. So now we get to K. 5 banks offer the same nominal rate on deposits, but A pays interest annually, B pays semi-annually, C pays quarterly, D pays monthly, and E pays daily. Okay, calculate the effective annual rate, or the EAR, EAR. Unfortunately, there's not a function for this, okay? So if something pays annually, then its effective annual rate is just the same as the nominal rate. Because it pays once a year, pays 7% that one time a year. But if something pays semi-annually, then it's going to be earning a better effective annual rate. Unfortunately, it's a little bit confusing. So the formula is 1 plus the nominal rate, the 1 plus the nominal rate, divided by the number of periods. So if it's paying semi-annually, there's 2 semi-annual periods in a year. So I'm going to put 2. And then raised to the power of, so in Excel, we use this little up caret, which is a shift 6, okay? Raised to the power of the number of periods minus 1. So remember our number of periods in a year, 2 semi-annual periods, so number of periods minus 1. So that is going to be, oh, that's not right. Oh yeah, we don't want to put this in parentheses, sorry. There we go. So 7%, but compounded semi-annually gives you an effective annualized rate of 7.12. So if we go to C, which is quarterly, which means 4 periods in a year, we're going to say this equals 1 plus the interest rate divided by 4, raised to the number of periods, which is 4 minus 1 power. And so if it compounds quarterly, then it earns an effective rate of 7.19. This one is monthly, so equals 1 plus the interest rate divided by, there's 12 months in a year, raised to 12 minus 1. And finally, daily compounding equals 1 plus interest rate divided by number of days in a year, 365, raised to the power of 365 minus 1. Whoa, did I put it in parentheses again? Oh no, I just put an extra 1 there. There we go. So you can see that the more we compound, the more an investment, the more the effective rate is, the more we're actually earning on the investment. All right. So our future value after 1 year. Okay. So if I say this equals absolute value of the future value of rate, 7%, number of periods, for when it's just 1 year, it's just 1. Payment, 0. And the present value, 3,500. So at the end of the year, my 3,500 turns into 3,745 with annual compounding. So again, if I want to come here and say, okay, if I want to be able to use my fill tool to just fill that over, what numbers do I need to stay locked on? And which ones do I want to move with me? So my first one is my rate. I want that to move with me, right? So when I pull it, I want this cell to be pulling the rate off of there. So I'm going to leave that alone. But there's no easy way to do that. So I may have to just hand type those in, right? My number of periods, unless I wanted to create a reference somewhere for those. The 0 will stay the same each time, and then the present value, we'll want that to stay the same each time. So now, if I grab this and fill it, it won't be perfect because I'll need to come in here and say, there's not 1 period. In the semi-annual, there's 2 periods. And in the quarterly, there's 4 periods. And in the monthly, there's 12 periods. Oh, something's off. Huh. Oh, you know why? Because our rate, well, that should work. Our rate, oh, you know what? Oh, yet so I was wrong about that. We don't want to adjust those. The reason is because we've already adjusted by changing the rate, right? By figuring out this effective rate, that already adjusts for the fact that there's the compounding. So I don't want to change the number of periods. So after a year at this effective rate, this will be the amount I've earned. So you'll see it gets higher and higher as we go across. But here now, we'll say this equals the absolute value of the future value of rate 70 or 7%, number of periods, I'm going to put 2, payment 0, present value 3,500. Whoops, I didn't put a comma. Present value 3,500. Now we should be able to. Oh no, we have to tell it to stay on that same present value. So we'll lock in cell B92. And now we should be able to use our fill tool. You can see it's actually not a huge amount of money more, right? Like, I mean, by the end it gets up there, but even after 2 years, it's about $18, something like that, more in interest you earn for that daily compounding. But of course, if you're a giant credit card company and you can get people's payments compounding that way and you owed billions of dollars, then it adds up to some serious money by the end, right? All right. So let's move on to K2, which is calculating the nominal rates um, that will cause the banks to provide the same effective rate of interest. So for this, we actually have a function in Excel. Why we didn't have one to find the year, I don't know. So the function is nominal. And for nominal, we just put the effective rate, which is right there, 7%. Oh, wait, sorry, I'm doing this for B. That's weird. That set me off. So we do the effective rate for B, comma, then the number of periods. So again, B is semi-annual, so it's 2 periods. So this will tell you that, is that right? That seems a little weird. Oh, no, no. So what we're, yeah, sorry about that. But for our nominal rate, so we're going to do, what we want to do is our 7%, 2 periods, and then it will tell us that if we're going to pay semi-annually, we will pay 6.88%, and that'd be the same as paying 7% once a year. So for C, well, it equals nominal. So the effective rate, again, 7%, but this one is quarterly, so it's going to be 4 periods per year. PERY means periods per year. For D, we're going to hit effective rate of 7%, and then the periods per year for monthly is 12. And then for E, effective rate of 7%, periods per year, because it's daily, 365. All right, there's our nominal rate. We're getting there. We're almost there. All right, let's take a look at part 3, calculating the amount of payment to be made annually for, annually, semi-annually, quarterly, or monthly, or daily for E. What was E up here? No, that's not be right. Oh, just E. I'm sorry, I'm just confused. So what we're talking about is 3,500 and the number of years. Okay. So I guess we're still using the same interest rate up here, 7%. So our payment then is going to be equals the absolute value of payment. The rate, we're going to use this 7% up here. The number of periods is only 1 year, so 1. The amount, or for the present value, Wait a minute. Sorry, we're going to put a 0 for present value. Then the present value, the future value is 3,500. And again, because this is, so what this is the amount of the payment we're making. So this one's going to be started calculating from the beginning of the period. You got to know that banks like to calculate money they owe you from the end of the period and money you owe them from the end of the period. Sounds like a bank, doesn't it? Okay. So when we do semi-annually, we're going to do the same idea, absolute value of payment, or PMT, where we have B9, B91. There's our rate. But now, because it's 2 payments per year, we're going to take that amount divided by 2. So I'm actually going to put that in parentheses. Right? Because we're not paying 7% per year, we're paying half of 7% per year. Number of periods is going to be 2 because it's semi-annual. Present value will be 0. The future value will be 3,500. And then 1 for beginning of the period because it's us making a payment to the bank. So we either have to make annual payment of 3271 or a semi-annual payment of 1661.74. So here's quarterly equals the value PMT where our rate is percent divided by 4 because it's quarterly. Number of periods is 4. Present value is 0. Future value 3,500. Type 1. That's what our quarterly payments would be. Equals absolute value PMT rate. We're going to take our rate. This time it's monthly, so divided by 12. Number of periods is 12. Present values. Ooh, what did I do? Present value is 0. And type is 1. Oh, I did something wrong. Rate. Number of periods. Present value. Oh, future value is 3,500. Type is 1. There we go. And finally, daily. What would our daily payments be? So equals absolute value. PMT. 7% divided by 365, 365 periods in a year when they're daily periods. Present value is 0. Future value 30. I didn't put a comma. 3,500. Type 1. Did something wrong. So there's my rate. Oh, I didn't close my rate. Okay, so in order to pay an amount equal to 3,500 in a year, if we pay at the beginning of the year and interest rates are 7%, we could pay 3271 in one payment or 1661 in semi-annual payments, or 837 in quarterly payments, or 280 in monthly payments, or 926 in daily payments. That's what that's for. And you can think about how that would get used in like a banking sort of situation. Okay, we're getting close, guys. Stick with me and I'll stick with you. So here we're setting up an amortization schedule. We have an original amount of a mortgage, interest rate, and then a term to maturity. So they're going to pay off $16,000 in 4 years with 8% interest. Okay. So again, we're going to use this function, the absolute value, PMT. The reason I do absolute value is because payments will come out as negatives because that's money you're paying out. It comes out cleaner with absolute value. Payment. All right, PMT. And then our rate right there at 8%. Number of periods, 4. And the present value is the 16,000. So our payments are going to be $4,830.73. So that will help. That will pay off the 16,000 that you owe with 8% interest over 4 years. So here's how we make an amortization schedule. So our beginning balance is what we owe at the beginning. So that's going to equal the 16,000. Our payment is what we just calculated right here. In fact, our payments stay the same all the way through because we make the same payment each year. The amount of interest is going to be the amount of our beginning balance times the interest rate. So that tells us out of this whole payment of $4,830.73, $1,280 is interest, and the rest of it is going to go to pay principal. So it's going to be payment minus interest is going to be the repayment of principal. And then our ending balance will be our beginning balance minus the amount of principal we paid off. Our beginning balance for the next year, is this going to be the same as our ending balance for the first year? Then we'll find our interest by saying this equals the balance of that year times the interest rate. Our repayment of principal will be the total payment minus the amount that is interest. And our ending balance will be the beginning balance from that year minus the repayment of principal for that year. Third year. Now we could use the fill tools for this, but I'm just doing this so you can see it done a few times in a row. I know it's getting long here. So our beginning balance is the same as our ending balance last year. Our interest is going to be our beginning balance times our interest rate. Our repayment of principal is going to be the total payment minus the amount that is interest. And our ending balance will be our beginning balance minus the repayment of principal. In year 4, beginning balance will be the same as the ending balance from year 3. The interest will be beginning balance times the interest rate. Payment of principal will be the payment minus the interest. And then the ending balance will be the beginning balance minus the repayment of principal. So it's fully paid off. So that little table I made there is called an amortization schedule. Anytime you borrow money or you lend money to someone, when you borrow, they will give you an amortization schedule to show you how your payments are going and how they're calculated. And then at the end of the period, you can know how much you owe each time. If you ever loan money to somebody, it would be useful to do the same for them. All right, last one, very last thing. Create a graph to show how the payments are divided between interest and principal repayment over time. So really, I'm just going to highlight my payment and interest. I'm going to go up to insert. I'm going to insert some type of a bar chart. Those amounts look a little weird. We'll try this. A bar chart. Why does that look like it's higher than 5,000? How much is the total payment? Oh, I know why. You know what I'm doing? I'm highlighting payment and interest. So I should be highlighting is interest and principal, because those are the two amounts that are actually going to go into um, my payment, right? So let's try that one and see what it looks like. Oh, that looks pretty good. Comes up to just under 5,000. You can see how much is interest, how much is repayment of principal. Throw that in there, and I finished my chart. Okay, I know that was long. If you stuck with it all the way through, I'm proud of you. If you had to do it in multiple sittings, I'm still proud of you, because that was a tough one. But I hope you got more comfortable with Excel and with just some of the concepts of the time value of money. So have a great night, and sorry it was so long.